So let's start.
Okay.
Well, first, let's recall what we did last time. Last time, as before, we were studying theta functions, which is defined by a series like this. Well, this is already generalized theta functions with characteristics, which we will use to construct Jacobi elliptic functions. But theta functions has good case of periodicity like this. And we know where their zeros are. And using those properties, last time we proved this quite non-trivial equation of Jacobi's theta relations. Here, x is just variables, and y's here are defined by this, namely these essentially sums of x's. There are, yeah, we can prove this in various ways. For example, we can compare periodicity of both sides, and we can check that they have the same zeros. But more direct proof, probably due to Jacobi, is just to expand these products into sums like this and compare Fourier coefficients. Because of the good property of this matrix A. Or in other words, this coordinate transformation is quite nice. We can write such sum. Hello? Oh. Such sum into products. And that was the proof last time. And well, there are a bunch of variants, and among which we need the following three. By shifting variable x1 by some value, some signs change compared to this original relation, and correspondingly this theta function is replaced by some other theta functions with characteristics. And the more complex, complicated looking variant is this. Actually, the proof is almost the same. We just shift all variables. Now, of course, we don't need to remember this. There are tables for such things. And yeah, from these relations, we can deduce several formulae, like additional formula for theta functions. For example, this gives theta 0, 0 for x plus u times theta 0, 0 for x minus u can be expressed in terms of theta functions with arguments x or argument with argument u. There are three formulae here, but there are tens of formulae of this kind. And they are obtained by specializing these formula, some variables of these formula, like this. And we want to show this Jacobi's derivative formula. And for that purpose, we proved heat equation for theta functions last time. Well, it's very simple because this series defining theta functions converges absolutely and uniformly on some domain. We can differentiate this series termwise. And the termwise differentiation is very simple, like this. And we get certain coefficients. And the only difference of these two derivatives, one is second derivative by u, one is first derivative by tau. But independent part, this one and this one, are the same, and only coefficients are different. So summing them up, we get a heat equation. Exactly speaking, complex heat equation, because the heat equation in physics takes values in real numbers. So when this variable is real, and when this tau modulus of theta function is purely imaginary, we can rewrite this heat equation by such real valued theta function, which is the real authentic original heat equation in physics with certain value of our term conductivity. Okay. Up to now, that was what we discussed last time. Now, let's proceed. One of the fundamental equation which Jacobi proved is this one. So recall that theta function is even as a function of u when the characteristics is not 1, 1. And this function is odd. 1, 1, eta. So if we expand this function around 0, it has such a Taylor expansion. Since this is an even function, there are only even powers of u, while theta u, theta 1, 1u, or well, theta 1 has such Taylor expansion. Because it is odd function. Odd function has only odd powers in U. And this equation gives relations between the first terms of these expansions. Well, this is a corollary of one of the equations which we proved last time. J3 is this quite complicated looking formula, but if we specialize variables like this, especially this is important. 3 variables are fixed to 0. Then what happens? If we fix x4 to 0, then here is theta 1, 1 of 0. So this is 0. So this part, this amount vanishes. Here is the theta 1, 1, and here is theta 1, 1. So if we put x2, x3, and x4 to 0, then only remaining term is this one. Well, this part remains, all terms remain, and if I fix like this, then old yj is something like this. So if we fix them to 0, then this all of them is equal to x over 2. So we get such an equation. Well, yeah, it's still far from this equation, but let's put this Taylor expansion to both hand sides. Now, for example, this, well, as I told you, this is yeah, perhaps I forgot to tell you that this note, this symbol without parentheses is just zero values of theta's. Well, the theta 1 prime is the derivative. Of course, we can write zero here, but it's a bit lengthy. So let us use such notation. And then, well, yeah, this is theta 1 prime x plus 6x cubic plus like this. And this is our theta 1 prime x over 2 plus theta 1 plus 6 triple prime and x over 2 cubic plus etc. And for example, this is theta 1 0. So this is constant. And theta 1 0 double prime of 2 x over 2 squared, and so on, and so on, and so on. So, for example, the first term is product of this theta 1 prime x times this constant. So this is theta 1 x times theta 1 0, theta 0 1, theta 0 0, and the right hand side becomes 2 here, and so x appears here, and all the other terms include x more than twice. So we have theta 1 prime 1 over 2 from here, and the other constants. Well, this is trivial or identity. So the first term gives us no information, but their second coefficients, namely coefficients of x cubed, is essential to us. The first term is, the left-hand side gives this, and the right-hand side gives this. Where 1 over 24 is 2 here times 1 over 6 times 1 over 2 cubic. And this comes from theta 1 prime x over 2 here, and for example, this comes from this. Etc. So this this term comes from this, and second degree term here, and constant. Oh, the result is a bit lengthy, but the structure is very simple. If we divide both hand sides by theta 1 prime and theta 1 0 0 0, and with some arithmetics, we get such an identity. And here plays the heat equation important role. We have second derivatives of this and third derivative, namely our second derivative of the first derivative of theta 1. So these second derivatives can be replaced with first derivative by tau. And this third derivative of theta 1 is replaced by first derivative by tau of first derivative of theta 1 by u. So by canceling this 4 pi I, we have such a formula, which is equal to this logarithmic derivative of this quotient. What does this mean? This means that this does not depend on tau, or in other words, such a ratio does not depend on tau. So we are already close to this formula. The only thing we have to do is to find this constant, namely this ratio. But as this is constant, we can substitute any tau or make tau to infinity. Exactly speaking, we can move tau to infinity in this direction. In other words, such a quantity goes to 0. Well, this is equal to real part of n, which is equal to so if our imaginary part diverges, q goes to 0. Actually, this quantity is very fundamental because when u is fixed to 0, then this is definition, u becomes 0. So essentially, we have series in Q. For example, this. And if u is 0, then we count this and this. So what is this? This is and this. What does this mean? When n is 0, it is just 1. When n is 1, this is q to 1, q to 1. When n is 2, so this is bilateral infinite series. And we can regard this series as a Taylor expansion of some function around this point. And the leading coefficient, leading term of this expansion is of course 1. For theta 0, 1, it is the same. Actually, we have some signs. But the leading term is 1 as before. Well, for these two series, the things are a little bit more non-trivial. So because we have such definition. The 0 value is this, and this means that when n is 0, it's q2 1/4. And when n is -1, this is -1/2. So we have again q2 1/4. And the next term becomes n is 1. This is 3/2. So something like this. So the leading terms are this. And for this, the idea is the same. Just we have to differentiate this series by u and then put u to 0. So because of such coefficients, we get such a leading term. And we'll return to our program. We want to find this constant. So just put them into this, and the numerator is just like this, and the denominator becomes like this. So when q goes to 0, it is just -1. no, sorry, minus pi. So we obtained such a good relation. As I told you, there are many different notations of theta functions like this, or maybe some theta function is defined by pi or something like this. Or maybe 2 pi, I don't remember exactly. And in such case, this coefficient might change. In some literature, you would find 1 here. So theta 1 prime is just product of these 3. Maybe in other literatures, this is just minus or just pi or something like that. It's just because of the difference of definitions, not a very serious problem. The important thing is that the derivative of this odd theta function can be expressed as a product of other 3. Okay. And so this is the end of the tutorial about theta functions, but just a remark on theta functions. And this is very fundamental objects. Well, we introduced this by saying that their Kesa periodicity and homomorphism, the condition of homomorphism are too strong, so just compromise and we introduce certain Kesa periodicity. But actually, theta function has more important fundamental meaning. For example, in algebraic geometry, theta functions are used to, for example, embed compatible surface into projective space. In numbers theory, actually, such Q expansions of zero values of theta are very important. We can, for example, we can count the number of solutions of certain Diophantine equations. In representation theory of, for example, Kac-Moody algebra, if you are familiar with integral systems, or probably you have heard about Kac-Moody algebras. And in that theory of, in the representation theory of such infinite-dimensional Lie algebra, theta functions appear as characters, generating functional dimensions of or representation space. Or in mathematical physics, for example, complementary theory or string theory, or theta functions appear in the computation of one loop correlation functions, etc. Well, so it's very important in applications, and also in the theory of elliptic functions, which we are interested in. It is also very important because any elliptic function can be expressed as a ratio of theta functions. Actually, this is very easy exercise if you know periodicity. Of thetas. Well, I use here theta 1, 1 on theta, but you can use any other theta functions with characteristics. So there are important condition is that there are two sets of complex numbers with the same number n of elements, A1 to AN, B1 to BN. And the sum is equal to, the sums are equal. Or maybe we can weaken the condition like this. This is a sum of integer plus integer times tau. Then it's easy to check that f of u plus 1 is f of u. And because of this, we have n minuses. Here, from here, also we get n minuses, so they cancel. And when u is shifted by tau, we get many factors like this. Actually is equal to various. Such factor comes from the numerator, and such factor comes from the denominator. And as you see, everything cancels. Here, sum of A's and sum of B's cancel because of the assumption. So we have an elliptic function with period 1 and period tau. On the other hand, so this is an elliptic function. And as you see, because theta has 0 at 0, so A1 to AN are zeros, and likewise B's give poles. On the other hand, we have prove that then there are same number of zeros and poles, and moreover, by a theorem which we proved probably 1 month ago, we have such a condition. So by using such property, f is expressed as a ratio of products of theta functions. So this is a general form of elliptic functions. On the other hand, so this is a function over elliptic curve, as we have argued. On the other hand, meromorphic function on P1 is a rational function. And we know that we can decompose polynomials into products of linear polynomial. And this expression of the elliptic function is an analog of this expression of a rational function. Okay. Now, let's proceed to Jacobi functions. Which we defined by elliptic integral long time ago. So what we have just proved is that elliptic function is a rational function of theta functions. So in other words, we can define SNs, CMDN, Jacobi elliptic functions, as a ratio of theta functions. And actually we can. Well, starting from the properties of SN and CN, we can get the answer, but here we first give you the answer. And let's check that such definitions rarely gives us what we defined before by elliptic integral. Well, first, let's see that they really define elliptic functions, which means that they are doubly periodic meromorphic functions. For example, let's say this one. Here, this is just zero value of theta as before. V is defined by this. And as we know, Sn is defined by sorry, modulus k. Actually, in our setting here, k is defined by a ratio of theta zero values. Later we shall check that this function really depends only on k, not just tau. So what we can say about this ratio? For example, theta 1 u plus 1 is minus theta 1 u. Theta 0 1 this is theta 0 1. So if V is shifted by 1, it gets sign. But if you shift u v by 2, then the numerator and the denominator return to their original value. So yeah, we'd better use v here. Which means, so this ratio has a period 2 as a function of v. So as a function of u, we have a period 2 pi times theta 0 squared. Likewise, we have another period because, for example, theta one has such a case of periodicity, and actually theta 0 1 has the same case of periodicity. So by the same argument, we have such a pairs. Well, so then that's the answer of this exercise. And well, thetas are entire function. Namely, they are holomorphic all over the complex plane. So the ratio is, of course, meromorphic. So we have proved that Sn defined by this equation is an elliptic function. Okay. And other two Jacobi functions, Cn and Dn, are defined in the same way. And just replacing numerator by other theta function. Actually, the pairs are a little bit different, like this. But anyway, they are elliptic functions. So what we know about Jacobi elliptic functions on R? For example, at 0, Sn is 0, and Cn and Dn are 1. How can we prove this? For example, if U is 0, then V is 0. But theta 1 is 0 at 0, so the numerator becomes 0. So Sn is 0. Other two proved similarly. Well, Cn is this, and V should be 0. So this is just a ratio of product of the 0 values like this, and well, they trivially cancel and gives you 1. For Dn, this is just the same. We have 0, 0 here, 0, 0 here, 0, 1 here, 0, 1 here. So we have checked these properties. Well, as we know, Sn was a function like this. Cn was a function like this. And Dn was well, well, what I want to say is that Sn is odd functions, Cn and Dn are even functions. Actually, it's really so because this is an even function. Denominators are theta 0, 1, so they are even. While numerator is here odd, here even. So Sn is odd and C and Dn are even. Other properties are like this. Or, well, we defined Cn and Dn by this formula over R, that's reflecting on some interval. But in our case, when we define Sn, Cn, Dn by this formula, this is for these relations are consequences of additional formulae of theta functions. Actually, first let's consider first one. By definition, we have such expression by thetas. So what we want to show is that the numerator is equal to denominator. But recall addition formula. This one. Sorry, this one. And oh yeah, I have already rewritten the formula here. And I'll put V here. Then we have V over and put 1 plus tau over 2 here and here. Then by transformation rules of theta functions, we have essentially theta 1 ones here and here. Actually with some multiplier, but they cancel on both sides. And well, theta 01 at 1 plus tau over 2 is becomes essentially theta 1 0. So we have this equation, and from here we have so moving this term to the left, we have here this, and this equals to this. Namely, the numerator is equal to denominator, which means that Sn squared plus n squared is 1. The second one, which defines dn over r, can be proved by similar formula. Well, in this case, we put 1 over 2 here. Then by shifting 1 over 2, we have, for example, such formula. So they become theta 01. So we have here theta 0, 0, etc. And so sorry, in this case, we use this one. So from this, we get this one. From this one, we have this. Because by shifting 1/2, so this theta 0, 0 of 1/2 becomes theta 0. And by dividing both hands by this, this, we have some extra factor here, but still, essentially this is this equation comes from this addition formula. And this part is Sm squared. And this is k squared by definition. And this part is Tn squared by definition. So we have proved this relation. Another important formula was this differentiation rule. Derivative of Sn is equal to the product of Cn and Tn. This is also a consequence of addition formula. Well, first, let's compute this derivative honestly. And don't forget that this argument is a multiple of u. Then, yeah, the definition was already. Yeah, but by the first year calculus, we get such formula. So, well, now we use the addition formula A3, which we proved last time. This is it. Essentially, by differentiating this by u and putting u to 0, we get such a formula. Or, in other words, this is equal to this theta expansion around P is equal to 0. This is equal to like this, and so on. And just by gathering the terms of the first order, from the left-hand side, we have this. And from the right-hand side, we have this. Well, here, we have such a simple expression because theta 0, 0, theta 0, 1, and theta 1, 0 are even. So it does not have a linear order, first order term. So this term comes only from here. So what we want from this appears here. So we can replace the numerator by such an expression. And here is the important part. This theta 1, 1 prime is, as we proved, product of other thetas. So this constant cancels. This constant cancels. Theta 1, 0 also cancels. So we have 2 theta 0, 1 above, and theta 0, 0 and theta 1, 0 are below. So we get this expression, and this is a product of Cn and En. So that's the proof of this differentiation rule. Okay. So what we proved is that derivative of Sn is equal to product of Cn times Tn. And Cn is square root of 1 minus Sn squared. Tn is square root of this. So we have such a differential equation for Sn. And by this we have when we solve first order equation, differential equation, ordinary differential equation, or in the first or second year of undergraduate course, often we use such a technique, right? And then integrate. Then this means that we integrate, so u is equal to such an integral, which means that Sn is inverse function of this elliptic integral. So that the proof that Sn defined by this ratio of theta functions is an inverse function of elliptic integral. Okay. So yeah, time is up. So today it's over, and probably next week we can finish this seminar, but I'm not sure. At least we have still another day. We have still 4th of June is the active day, but anyway, the most part of this course will be finished next time. So, okay, any questions?
Well, I have a question.
Yeah.
You know, in rest studies, you just consider the elliptic function on where, just on where, and how to extend to complex surface, just using the theta function.
Excuse me. Once more, please.
I see that in here you just consider the Jacobi elliptic functions on where, just on where, and but the title of your PDF files is the complex Jacobi elliptic function, and how to extend it to complex surface, just using the theta function. How to extend the elliptic function from where to complex?
From what?
From where? From R to complex surface.
Complex plane, or probably elliptic.
Oh yeah, complex plane. Yeah.
Well, actually, this expression this expression is valid also for complex plane or Riemann surface, exactly speaking, because we have square root here. So we should understand this integral as an integral over on the Riemann surface of elliptic curve.
But here you just consider it the integral on where? I think it is on where.
Or integral, this integral, you mean?
Yes, the integral, just the integral on where line? Or on complex plane? I think it's just on the where.
This is an integral on the Riemann surface.
Oh.
So.
Oh yeah.
We have two cuts. And so we are starting from 0. And we take certain contour connecting 0 and the Sn of u. Actually, well, first we'd better restrict ourselves to certain neighborhood of 0. Otherwise, because of the topology of the elliptic curve, we have multi-valuedness. So if we, for example, change contour from here to here, we have a certain difference because of the period of this one form on the elliptic curve. This way or this way. So first we should understand this equation as a equation close to close to 0. Actually, when we considered Sn over R, it was not a big deal because this was defined only on the real interval like this. So we integrate such function from here to some value. But on the complex plane or on the Riemann surface, we have such a non-trivial cycle. So this integral is multi-valued, as we discussed in March, probably. Because of the root here. So first extend, analytically extend this expression in the neighborhood of 0, which we can do because the expression is analytic. At least in this one form can be defined all over the elliptic curve on the Riemann surface. And so if we connect points close to the origin of the coordinate, there is no problem. We have a single valued function. And we can. So if we replace this, then this is a function of u up to z. Then we have an integral from z. This is a function. And so we take the inverse function to this equation, this function. And thus we can define Sn as a function of u. This was what we did at first in January or February. On the other hand, today we defined Sn by this formula as a ratio of thetas. So we have to match those definitions. And the reason why these two definitions coincide is the differential equation. That was what I explained you. So do you agree that these expressions are, these two equations mean the same thing? Just by solving this differential equation, we get this expression. Or by inverting this, we get this. So this is the usual method of solving the ordinary differential equation of the by separation of variables. So df to solve this kind of differential equation, we rewrite this like this and then integrate. This was what we done in the first or second year undergraduate course. This is what I did here. So then the keyword is separation of variables. So ordinary differential equations. So today there is a very sophisticated separation of variables by squaring, and it's a different thing. What we need is the undergraduate course on ordinary differential equations. So please have a look at some reference. And then you'll see that this can be solved by this integral.
Okay.
I have a question. Can you help me?
Yeah.
Sorry, yeah, I have a stupid question. You know,
Yes.
the Jacobi elliptic functions is the inverse functions of the first kind of elliptic integral. So I don't know what is about the second kind. I mean, the inverse
That's
function.
a very, very good question. It also gives, yeah, for example,
Yeah.
an elliptic function. I don't remember explicit form, but well, yeah, sorry, I cannot.
It's okay. There's can you recommend some references?
Probably you can find something in the famous textbook by Whitaker and Watson, A Course of Modern Analysis. Yeah, usually, yeah, in the textbooks of elliptic functions, this is somehow neglected, or yeah, theoretically it's possible to write down some explicit form, but it's yeah. Sorry, honestly speaking, I don't remember.
Okay, that's all right. Thank you.
Thank you.
Okay.
Any other questions? So then, see you next week.
See you.
See you.
You.
Thank you.
Thank you.